Okay, starting with number 5. I can't remember which page this is. This is the one that is out of order. If you start answering this question, you just go from here to here to here, you're going to hit a roadblock and you won't be able to go on. So I'm going to show you the order in which you need to do it, and I'll try to put it in the right order when the test comes around so that you don't have to figure this out. I didn't mean to make this tricky. The water's dropped on a forest floor from a height of 600 meters. So you ought to be thinking, dropped. Okay, something's falling. So I'm going to write this down. A equals negative 10 meters per second squared. That's just, always write that down. As soon as you hear about something being dropped or thrown in the air, that's its acceleration. That means, I'm not going to tell you what it means. I'm just going to write it. So the distance is negative 600 meters. Now, if you leave off that negative, you leave off this negative, you might be fine. And if that always works out for you, great. But to do it properly, the distance is negative 600 because the water is dropped. Downward is negative, so this is a negative distance that the water is traveling. And if you don't do that, but you do this and you get your signs mixed up, you might just run into trouble when you use the formula. So try to do it this way if you can. Average velocity of water, can't do that one yet. Let's go all the way down to this, which we can do. I already wrote that right there. That was just a reflex from seeing dropped. So I know the acceleration is this. And I can do this next one. Can't do these until I do this next one. The time for the water to hit the ground. Get out my formulas, looking for time. Here's a formula for time, there's a formula for time, there's one. But what I have is acceleration and I have distance. So the one I've got to use is this. So I write my formula, then I start plugging my stuff in. Square root of 2 times negative 600 divided by 10 meters per second squared. Multiply those out, I get negative 1200. Divide that by negative 10, and what I'm left with is a square root of 120 seconds squared. When you take the square root of that, you get right about 11, so that's the time. Once you get the time, then we can figure out these other things. We can go back up to the average velocity of the water, or we could do this one first. It doesn't really matter. I kind of like to do this first because there's an easy way of doing this after you do that. So for average velocity, this formula right here, this is average velocity. That's the first one we learned in this class. So it's V, and it's based on distance and time, which we already have. We've got distance, we've got time. So substitute in the distance, negative 600, time is 11 seconds, divide them and you get negative 54 meters per second. It's negative because the water is going downward. Now the final velocity of the water, one easy way to get that, if you have the average velocity, let me draw another picture. The water's dropped from up here, starts to fall. It's going to reach its average velocity about halfway through. So average velocity is 54 meters per second. It's not velocity, that's speed. The velocity is negative because it's going down. So it's not moving at all up here, and it's going to reach its average about halfway time-wise. So in the first half of its trip, it speeds up to that. That's how much that's how much it accelerates in the first half. It's going to accelerate by the same amount in the second half. So you're going to add another 54 on, and you're going to wind up with about 108 meters per second. If you just double the average, you get the final velocity. So you can see I don't have 108 written there. It's because of some rounding that I did. There's another formula if you don't like doing it that way. The velocity, you just start looking for velocity formulas. We've got distance over time. That gives you the average velocity. It's kind of tricky, isn't it? And then I've got this other one, velocity equals acceleration over time. You know, maybe I'll make a note in here that this is average velocity, and this is final velocity. This is final velocity after you've been accelerating for a little while. And this is average velocity when you've been moving over a distance in a certain amount of time. I think I should probably make that note on the sheet. But if I don't, those of you who are watching this, you'll know. So, V equals AT, the acceleration is this, the time is that. So that's the A, that's the T. You get negative 110 meters per second. Again, it's negative because it's going downward. The last part to fill in, we did these two earlier, this was first, then that, then this, then this. The last is just to convert this to miles per hour. And I don't care if you convert it exactly. I just want you to know that 1 meter per second is about 2 miles per hour. So take your meters per second and double them, and you'll approximate miles per hour. 110 meters per second times 2 is 220 miles per hour. Somebody pointed out water doesn't really fall that fast. You'll never have water falling that fast out of the sky. Raindrops don't fall that fast. But if there were not any air, they would fall that fast if they fell from 600 meters. All these problems assume that there's no air. So if you want to really know what the velocity is in miles per hour, 1 meter per second is much closer to 2.24 miles per hour. So you'd multiply by that to get the exact answer. Number 6, this is a rubber band car. It's the first part of this question I like. The second part I'm feeling a little less comfortable with, and I'll tell you why in a minute. So I don't think I'll put that kind of a thing on the test, at least not this one. The car speeds up for 5 seconds over a distance of 12 meters. So you let it go, it's speeding up, speeding up, speeding up. When the rubber band pops loose, it's gone 12 meters, and that's taken it 5 seconds. You've got to figure out the acceleration. So you've got a time, and you've got a distance, and you want acceleration, so you look for, here's acceleration, but that doesn't have distance and time. It's got velocity and time. This one, that acceleration formula has distance and time. So it's 2d over t squared. Write down the formula, start plugging stuff in. There's d, there's t. We're going to square it. Multiply these, you get 24. Square that, you get 25. And divide, and you get 0.96 meters per second squared. So that part works. The second part, I was asking you, what's the acceleration after the rubber band popped loose? And you can use the same formula, and it kind of works. It does work, but there's a little problem. You have the amount of time it takes it to stop, and you've got the distance that it takes it to stop. So we're going to be getting a deceleration now because it's stopping. So our acceleration should be negative. You'll see it's not going to be negative, and that's the problem. So we use the same formula because we have distance and a time. That's the new distance, that's the new time. 2 times that is that squared is that. Then we've got 1 meter per second squared. So, but it's slowing down, and if it's slowing down, then it shouldn't be 1 meter per second squared, it should be negative 1 meter per second squared. The reason this doesn't work, the reason you get that answer and not that, is because these formulas, these three, were derived based on a situation where you had something starting from 0 and then accelerating. And in this case, when the car speeds up, speeds up, speeds up, rubber band pops loose, then it slows down and stops. In this second half of the event, it's starting from a fast speed and then slowing down. So by using this equation, we're applying it to a backward situation, so we're going to get a backward answer. And it works, but I'm just not going to put that on the test because that's kind of iffy.